Hey everybody, Mr. Judson here. So for today, we have something that is actually kind of nice, I guess. We're still simplifying trig expressions, except they're going to change the wording just a little bit. What they're going to say is to verify that the identity they have written down is correct. And these identities will all be things that we haven't seen before. But the nice thing is, if they're asking us to verify it, what they're saying is some trig expression is equal to this. So essentially they're telling you the answer to the problem. We just got to get to the answer. And if we know what that answer is, maybe that makes the problem just a little bit easier. Okay? So I'll give you an example here in just a minute. But first of all, I just want to review some of the things that we have said are good strategies to try. So this might be one of those things where if you want to, you could pause the video and maybe do a little snippet of it and put it into a Word document or something and save it. But this is our goal right here, the first three. We're trying to get down to one trig expression if possible, no fractions, and one term. Well, really, these three don't really matter as much to us today because they're going to tell us what the answer is. We just have to get to their answer. And so it's these strategies that we want to make sure we pay attention to. So same as always, if you're unsure what to do, convert to sines and cosines. If there's an exponent of 2, we want to think about using a Pythagorean identity. Factoring, we've done a little bit of this, but not a huge amount. So try factoring the expression, that might help. When you see fractions, find the least common denominator, add the fractions together or subtract them. And this one, if there is a complex fraction, multiply every term by the least common denominator. There's also one other strategy that's not written here, and that is this. Multiply top and bottom by the conjugate. Multiply top and bottom by the conjugate. And sometimes that'll help us get what we're looking for as well. All right, so this is what today's problems will look like. They'll ask us to verify that this is true. And one of the things that I think you always want to do with a problem like this, this almost seems backwards, but in the long run it makes it easier. You want to pick the most complicated side, which appears to be this one, and make it look like this. Okay? Start with the more complicated side and turn it into something easy. That's a lot easier than taking something simple and trying to make it more complicated. Going from here to here, I think, would be a more difficult problem. And then one more rule that we want to make sure we're aware of is when we verify something, we need to pick one side to work with and then only work with that side. So if I'm trying to work with the more complicated side, what I'm going to do is I'm going to start here and essentially simplify this expression until I get to a sine squared theta, which is what we have written here. Okay? So it's just like what we did the last 2 days. We want to simplify this. I'm just telling you guys that's the answer. You guys go ahead and try it. All right, so another thing that I want to point out, and this is really important here, is there will be multiple ways to do this problem. Okay? I may do it one way, and you guys might think of something totally different, and they could both be correct. Okay? Sometimes I've seen 3 different ways to do the same problem, and they don't look anywhere near the same. So don't think that if I do something different here, what you did is wrong. I'll try and go through different methods if I see them. So one of the things that I see first is that if I break this down into 2 different fractions, I would have a secant squared theta over secant squared theta minus 1 over secant squared theta. And then since that's the same top and bottom, that's really just equal to 1. 1 over a secant is really a cosine of theta. So 1 over secant squared, that's a cosine squared theta. And now I look at that and say, well, that looks like one of our Pythagorean identities. Sine squared plus cosine squared equals 1. What I have is 1 minus a cosine squared, so I'll move the cosine over to this side. And so that right there really is equal to a sine squared of theta. And I always like to draw an arrow back to whatever it is we're trying to show. And so there it is. I have verified that that is true. Now, that didn't have too many steps involved, but somebody else may have said this. Somebody else may have said, well, I'm just going to change the sines and cosines right off the bat. So I'm going to go 1 over cosine squared theta minus 1 over 1 divided by a cosine squared of theta. And so we could look at that and say, well, that looks like a complex fraction. I've got fractions within the fraction. And so what I'm going to do is I'm going to multiply everything by the least common denominator, which is just a cosine squared. So I'll multiply this by a cosine squared theta, this by a cosine squared theta, and this by a cosine squared theta. It's each term, not top and bottom of each term, okay? So here, those cosines cancel, and I get 1 minus a cosine squared theta over here. These will cancel, so in the denominator now I just have 1. And we just saw that from our Pythagorean identity that this is equal to a sine squared theta. And we got it done. Now again, here's a third way to do this one. Let's say somebody looks at this and says, well, secant squared minus 1, I think that's a Pythagorean identity. So let me do my chicken scratch. It's tangent squared plus 1 equals a secant squared. So if I want a secant squared minus 1, I can move this one over here. Have secant squared minus 1. So this is really equal, this numerator is equal to a tangent squared. So I'm going to go tangent squared theta over secant squared theta. And so now I'm kind of stuck, so I guess I'll go to sines and cosines. So a tangent would be sine over cosine. So that means that becomes sine squared theta over cosine squared theta. A secant squared is 1 over a cosine squared theta. And so now I'm doing a fraction divided by a fraction, which means I want to multiply by the reciprocal. And so a sine squared theta over cosine squared theta times, flip that over, you get cosine squared theta over 1. Those cancel, and I got a sine squared theta. So there's 3 different ways to do just that one problem. And maybe somebody did it differently. But if you feel like your logic is correct, and you were able to go through and get to a sine squared, well then it probably is. Now, one thing you have to be real careful about problems like this. This happens all the time. Someone's working through the problem, and just say you just get to right here, and they don't know what to do. So I'll just say, yeah, that equals a sine squared theta, because that's what I'm supposed to get. Well, that's kind of cheating ourselves out of the process. We all know we're supposed to get here. So there's no points for writing this down. It's all the steps in between. And so we just want to make sure that we have a logical reason as to how we're getting to this. I don't see a logical progression from here to here. So, if this was a test question and I saw this, I would stop right there. I'd give you credit for getting from here to here, but I wouldn't give you credit for getting farther. Okay? All right, let's try another one. All right, so you guys go ahead and try this one. So, You know, obviously this is the more complicated side, so I want to work with this one. I'm trying to make it look like that. And what I see is two fractions, but somehow at the end I get down to just one term. Well, the only way that's going to happen is if we get a common denominator and add these together. So let's go ahead and do that. Over here I'm going to multiply top and bottom by 1 plus a sine theta. So 1 plus sine theta. Make sure you include the angles in there. Okay? Don't just write 1 plus sine, we want to put the angle in there. And then this side I'm going to multiply top and bottom by 1 minus sine theta. Alright, so this is now my common denominator. So I'm just going to write that down. 1 plus sine theta times 1 minus sine theta. In the numerator I've got this numerator plus this numerator. So I've got 1 plus sine theta plus 1 minus sine theta. And so these two signs in the numerator will cancel each other out. So now what I have is 2 over, I'm going to go ahead and multiply these two factors together. I'll FOIL this. So I get 1 minus a sine theta plus a sine theta. Those will add up to 0. And then minus sine squared theta. The moment I write down that exponent, in my mind, I should be thinking Pythagorean identity. That's going to have to do with one of those. So I'm going to do my little chicken scratch thing. Sine squared plus cosine squared equals 1. I want 1 minus a sine, so I'll move this sign over here and subtract it. And so that should be equal to a cosine squared in the denominator. So now I have 2 over cosine squared theta. And by the way, the moment I wrote down this 2, I think one of the things that's really important about these problems is you're constantly looking back up here at what you're trying to get to. The moment I saw that 2, I was thinking, I must be doing something right. I'm getting close to whatever I'm supposed to get. Since I changed to sines and cosines, you know, here I see a secant, I'm kind of expecting to see 1 over a cosine squared of theta, and sure enough, that's what I have. So remember on Tuesday I told you guys you can just move that up above the fraction bar and it just becomes the reciprocal of this function. The reciprocal of a cosine theta is a secant theta. So this now equals 2 secant squared theta, and that's what we were trying to get to. I can't really think of a different way to do this one. I mean, you know, if you would have thought at the beginning change the sines and cosines, well, we already have that. I really don't even know what you could do. I mean, if maybe somebody thought conjugates, well, that's really what I just did here. I multiplied top and bottom by conjugates. So I would think this one, most of us probably did the same thing. All right, let's try another one. All right, so when I look at this one, yeah, which side is the more complicated side? Well, neither one. They're kind of both the same. If I really look at this, it kind of almost looks like if this is really equal to this. And by the way, this is important. They will never ask us to verify something that isn't already true. Okay? But just looking at this, if both sides look exactly the same and I'm doing the same thing, some people might look at this and go, oh, that means a sine of theta is equal to a cosine theta. Well, we already know that's not true. We saw points on the unit circle where the x-coordinate and the y-coordinate were not the same. So we know that's not true. So yeah, you just got to pick one side. When I can't decide, I just usually go with the left side. And I try to make this look like that. You guys go ahead and try. So remember, one of our steps here that we haven't done a lot of, but we always want to think about, is try factoring. See if you can factor an expression, because a lot of times that helps with these kind of problems. So when I look at this, I'm thinking to myself, I can get a sine squared out of both of those. So if I factor a sine squared of theta out of this term, I'm left with 1. Out of this term, I'm left with a negative sine squared theta. And now I'm thinking Pythagorean identities. Right? Here's my chicken scratch again. Sine squared plus cosine squared equals 1. So a sine by itself, if I move this over, I get 1 minus a cosine squared. So let me write that down. This right here is going to become 1 minus cosine squared theta. And then 1 minus a sine squared theta. So what if I would have just moved the sine over to the other side? I could have said that a cosine squared is equal to 1 minus sine squared. So that thing right there is equal to a cosine squared. And so now I just have to distribute that. And what I get is cosine squared theta minus cosine to the 4th of theta. And that's it. There we go. We're done. So that looked like it might be a difficult problem, but really it wasn't bad at all. We just had to think factor and then use our Pythagorean identities. All right, so here's our assignment. I think I got it right, number C9. Page 387, we're going to do 1 to 21 odd. As far as office hours go, I had a successful meeting today on Teams with Central Washington students. I wish more of us would have been there. There are 54 of us signed up for Central Washington credit. We had 17 people at the meeting. I'm going to try and start doing office hours, which office hours in terms of college is a time where a teacher is available to ask questions. And so what I will do is on Tuesday and Thursday, I will set up a Teams meeting, and I will invite you guys to participate, but really it's only if you have a question, okay? If you want to pop in and just see what's happening, you can do that. But maybe someone's like, Judson, I got stuck on number 17, can you show me how to do that? And I'll do that through a Teams meeting. I'm not exactly sure how I'm going to do that yet, but I'll find a way, okay? And so, you know, maybe I'll just hold a whiteboard in front of my computer screen. I don't know. But that's the idea, is that you guys just have the opportunity to ask questions. Another common question is, how are we doing attendance? Well, as long as I have had some kind of interaction with you guys during the week, then I mark you as present, okay? So several of you retook the exam. I know who retook it. You sent me emails. You're present. You don't have to do anything else. I have some ways that I can go to my Sway page and I can see who has been looking at documents. The one thing that I'm still struggling with this is many people have become subscribers on my YouTube channel, and I don't really know what that means technology-wise. I mean, I know it means you're watching, but I don't know exactly what a subscriber is, and I don't know if I have the ability to go and look and see who my subscribers are and what they've looked at. So people who are watching the videos that way, a little more difficult for me to find out. I told one student, if you want to, maybe Thursday near the end of the week, just send me an email that says, hey Judson, here's what I did this week. And that will be checking you in for attendance. That means, you were practicing what you're supposed to do. Don't make it up. That's one of the questions that came up with teachers is someone's going to send an email that says, hi, I'm here. Technically, is that good enough? Yeah, but please don't do that. Tell me what you're doing. I worked on this week. Even if you told me you did watched videos from 2 weeks ago and started working on the homework, That's okay to me. That says you're engaged. You're trying to get things done. Do I want you to keep up and do 2 per week? Yes, absolutely. But just, send me something that says, here's what I'm doing. I really only have about, 6 to 8 people I'm worried about. I haven't seen their name pop up anywhere. And I'm worried about those individuals, that they've just kind of blown things off. In my personal opinion, those who do that and they get a C out of the class, really, that's not really fair to those who have worked hard and got a C or a C plus. That just isn't fair. But I don't get to have a say in that. That's our school district making rules, and we have to follow it, and that's the way it is. I guess we're all learning to live with things we don't like, so add one more to the list. All right, that's it, you guys. Have a good weekend. Stay safe. I'll see you later. All right, bye.